Do you guys have any questions? We have covered ArcTangent, ArcCosine, ArcSine in great details. Today we can touch on cotangent, which is going to be similar to tangent and arctangent, okay? Because I have some questions in trick 7a for you to work with, okay? The basic ideas are pretty much similar, okay? And so I'm going to spend just a little bit of time with you on that. Do you guys have any questions? Do you guys have any questions? No? Okay. So the first part I like to work on to go over cotangent. But before that, let's do a recap. Okay, recap. We have pretty much followed the same theme about functions and inverse functions and so on and so forth, right? So this recap, okay, good morning, Christopher. So when we recap on sine, for example, right? On sine. Let me reduce the number of rows, right? See, we understand when we're talking about sine, the sine function we meant to are the sine function with domain from negative infinity to positive infinity, right? And its range, so that's a domain and range. So let me put a D here. Okay, and the range we have multiple forms, right? -1, 1, but I was telling you this is the least useful, right? This is the least useful. And the other two forms are from -1, between -1 to +1. Okay, and the next form, of course, the absolute value form. Less than equals 1. So all these are the three forms. The first one being most useful. Okay, the second one, second useful, and the last one is the least useful. They're all useful. They're all useful in their in applications. Okay, but this is whenever you see sine, this is the sign that's referred to. So there's no need for any confusion. There's no need for any confusion. But then when ArcSine is referred to, right? So let me insert another row. Okay, to clarify certain things, to emphasize some of those important things. ArcSine or sine inverse. Okay, let me make it 175%. All right, so sine is a function that would take angle as input, produces output, which is a ratio. It produces a ratio, right? What kind of ratio? For sine ratio, right? And ArcSine, however, takes ratio, produces what? Produces angle. Okay, so ArcSine, or that one, it produces angle. Okay, but these two functions are not inverse to each other. They are not inverse to each other. So what's the inverse for ArcSine? The inverse for ArcSine is another function. It's another function. Okay, the other function also doing angle to ratio, right? It's also doing angle to ratio. And the domain, however, Okay, the domain, however, for that sine is between negative pi over 2 to pi over 2. Okay, and then, and of course, so these two are inverse to each other. One's domain is the other's range. Okay, so this guy will be the range for its inverse. Okay, so this range, this domain will be the range here, and the range, then the domain for the ArcSine function will be from -1 to +1. And that will also be the range for the other guy. Do you guys follow me? So that's what we already summarized, and we have pictures and stuff. So when you do the summary, you want to attach the pictures to it, and the picture separate and picture together. Okay. So now for cosine, okay, for cosine, it's the same thing. For cosine is, I would say, similar. I should not say the same thing. Okay, similar. Okay, cosine is similar. But cosine, okay, so there's a sameness here. Cosine is taking angles to ratio, and the ratio, of course, is the cosine ratio. So domain from -infinity ranges from domain from -infinity, the range is also from -1 to +1. So that's cosine. Okay, and ArcCosine, however, okay, ArcCosine also takes, okay, takes ratio, of course, takes ratio and produces angle, ArcCosine. Domain is same, but the range, however, is 0 to pi. Okay, if you recall that piece, right? And these two are domain range to each other. Okay, domain range swaps, right? And of course, this is a cosine. This is the cosine. Well, I have given you these inequality forms. I have given you these inequality forms. Okay, these inequality forms reflected on here, okay, on the ArcSine part, right? So on the ArcSine part, so there are other forms to express that. So the ratio is going to be between -1 to +1, or the absolute value of x should be less than or equals 1. That's for the input, the ratio. Or you have -1 less than or equals to x less than or equals to +1. Okay, so these forms. And the range, we have the interval form, which we said oftentimes is the least useful. And we have all these other forms. Okay, between -pi over 2 okay, -pi over 2 less than or equals to ArcSine and less than or equals to pi over 2. All right, over here, remove that. Or the other form, okay, the absolute value. These are the forms that you often see it. You often see it. Then you wonder what does that mean, right? That's what happened to our student when they're taking, future classes. They only recognize one form and they don't understand the others, which becomes become the obstacle to understand the whole of the context, right? So that's why I'm going to give you these forms. So these forms, right, to describe the range of ArcSine or sine inverse interchangeably, and for that part as well, right? It's similar, but this part, they're all described over here. Okay, so I'm not going to repeat that. Now, the ArcCosine, the range, right? The domain part for ArcCosine, they're similar. They're similar. they're similar. Okay, absolute value of x less than or equals to 1, x between -1 and 1, and the range part that is ArcCosine is between 0 to pi. So this form may be needed for your future applications. Okay, this form. Does it have an absolute value form? Yes. Okay, does it have an absolute value form? It does. But it's a little bit, I think, well, I can give it to you now. I can give it to you, okay? It is like this. Okay, it's ArcCosine minus pi over 2 less than or equals to pi over 2. There's not a whole lot of application to it. Depends on, but depends on the depth you learn in calculus. Okay, I don't anticipate you are going to use this form very much, but I give you this form just as a you know, a coexisting form, a comparison point, a form for ArcSine. Okay, so that's about sine, ArcSine, and so on and so forth. As we mentioned earlier, right? As we mentioned earlier, that these two forms are referred to. These two forms are referred to. And these are often not even used because we will refer to these. In the case we need to refer this, we will just mention it's between -pi over 2 over 2. Like in the situation we have gone over about the special properties, right? For example, what are the special properties we're talking about? Right? The special property we talk about, such as sine of ArcSine, x equals to x for what? For x in the interval of between -1 to +1, right? That's one form, which is the first line in the table, the first table in trig 7a, and the other form would be ArcSine of sine equals to x for x in the interval between -pi over 2 to pi over 2. This is the situation. This is the situation that we say it's otherwise specified. Okay, it's always referred to the sign as we know, unless otherwise specified. So this is how we do the otherwise specified. Okay, for cosine is similar. For cosine is similar. Okay, for cosine we will have similar properties, right? You have a cosine of ArcCosine of x equals to x, and for the same reason, So you can see that, right? And the next one is ArcCosine of cosine equals to x equals to x. That's for x belongs to not between -pi over 2, not between -pi over 2 to pi over 2, but in the interval of 0 to pi. In the interval from 0 to pi. So we also have comparable two other properties out there. And next is tangent and arctangent, right? So I did not put the pictures in place. You guys can go back to study the picture, to bring the pictures together as part of your review, right? So I'm not going to do that here, but you are encouraged to do it. How about tangent, right? Tangent is interesting. Under normal circumstances, the tangent we refer to, right? We refer to, you know, of course, is angle is the input and the tangent as a function, right? It produces, hold on. It produces tangent ratio. It produces tangent ratio. Okay. And the domain of tangent, as we have talked about many times, right? X, the angle input can be any real number. Can be any real number. But the odd number multiples of pi over 2. The odd number multiples of pi over 2. Okay, and the range is all real numbers. All real numbers. Okay, we went through all that process. So we're making this table is not for you to memorize. No, it's to collectively put everything together in your mind. And have a full and better understanding of the consistency, the beauty. Well, let's remove the word beauty. It's just the consistency, excuse me, and so on, right? So that's the function we refer to. Arctangent, however, as we understand, arctangent is a function that takes ratio, right? And then arctan or tan inverse. Okay, these are used interchangeably. Okay, there's a little negative sign there. You know, sometimes it shows, sometimes it doesn't. It's so strange. But anyway, with that said and done, so it takes a ratio, but these two functions are not inverse to each other. They are not inverse to each other. This guy does not have inverse. Okay, this guy has inverse. Its inverse is tangent. Okay, still take angle to ratio. And it has, these two are inverse to each other. These two are inverse to each other, okay? So this is the whole thing we're trying to convey, which is a similar, all of these questions are similar in nature, is that from one takes ratio to angle, the other one takes angle to ratio, and this pair is inverse to each other only after we have specified the domain. The domain is between negative pi over 2 to pi over 2. But comparing with, you see, I put a tangent right underneath sine, right? In comparison with sine, with tangent, for sine, for ArcSine, the range is negative pi over 2 to pi over 2. That's it's inclusive, include the endpoints. But for ArcTangent, right? This is the range. So this is the range. And these two, okay? And the domain here, the domain for ArcTangent is all real numbers. And this range is also all real numbers. You follow me? But this last one is rarely mentioned, as always. So when otherwise specified, we also have these two forms. So what are these two forms? These two forms will be tan of arctan. Okay, and that should equals to x, okay, for any number in the domain of arctangent, right? The domain of arctangent is from negative infinity to positive infinity, right? So this is actually unconditional. It's always true, okay? So that part we have covered. And the next one is tan of arctan, no, sorry, arctan of tan. This group, okay? I can use X, I can use A, so let me use X, right? X now has a different meaning, it's angle. And this is going to be the same as X provided, okay, this is the otherwise mentioned, provided X is from negative pi over 2 to pi over 2. Right, so these are, you can see there's some similarities between sine and ArcSine and ArcTangent, right? I mean similarities, not the same. They're not the same. It's on the range. It's on the range. The range for ArcSine is between negative pi over 2 to pi over 2 inclusive. And for ArcTangent, the range is between negative pi over 2 to pi over 2 exclusive. Exclusive meaning negative pi over 2 itself and pi over 2 are not included. Okay, so with that comparison, how about cotangent, right? So this comes to what we want to address today about cotangent, right? Cotangent, of course, A. Okay, so I want you guys to refer to the things we've done for cotangent, right? We've done cotangent, except that this time is a cotangent. It still take angle, produces a cotangent ratio. And what is the domain? What is the domain? The domain, of course, if you know that cotangent equals cosine over sine, so the x coordinate of sine would be excluded from the domain of cotangent, okay? So the angles can be any real number, but k pi, okay? So review that part, okay? Review that part if you have questions here, right? We have addressed all of these issues before, and the range, right? We have done the graph for cotangent, for tangent, I'm sorry. The range is from negative infinity to positive infinity. All right. And the ArcCotangent function obviously takes ratio. It's a cotangent, it will be regarded as a cotangent ratio and goes through ArcCotangent and produces an angle. So similar. And its inverse, right? These two are not inverse to each other. Okay? But ArcCotangent has an inverse because it's rarely talked about. And that function is still doing the, doing the same ratio thing, but the domain will be 0 to pi. So that tells you the range for ArcCotangent is from 0 to pi. So there's a little similarity to cosine. And the range for this cotangent, of course, is still the same as here. And the domain for ArcCotangent then is from all real numbers. So that's about the cotangent, right? Of course, we haven't done cotangent in details, but here is the summary for all of them. You can see there's some similarities. So for cotangent, okay, so I'm gonna just briefly go over with you on the cotangent, how it has come about, right? Because if you look at the cotangent, right? Okay, so we have the conclusion for cotangent here, right? So we just have to go over the ideas, which is similar, right? So what is a cotangent? Cotangent. if we graph that, this is a cotangent curve. This is a cotangent curve. It's at your fingertips. Okay, it's at our fingertips. Okay, but how do we identify points and able, that's a whole process. We're not going to go in great details, but I'm going to give you the answer. Okay, each step of the, on those critical steps, right? Cotangent, this is how we analyze it. Okay, it's a cosine A over sine A, right? Sine A cannot be 0. That's why we exclude the points, make sine A equal 0, which is the x, the x intercept for sine, right? You see the logic? Do you guys hear the logic? So when we determine domain, we will decide, we're going to try to find, this has to be guaranteed. And the opposite of it, that's the opposite of it is sine A equal to 0. Sine A equal to 0, that give us the x intercept. So that's how the domain cannot be k pi. Okay, cannot be k pi. So how is that related to what we do here in the picture? How is that related to what we do here in the picture? Well, those are the numbers it cannot be, because domain can be any real number but k pi, right? So we let a k pi run. Okay, we let k pi run from 0, +1, -1. So these are the points that it cannot be the input, right? Not using heart. We don't like that. Okay. So what are the points that cannot be? 0, it cannot be. That's one of the k pi. Okay. Pi cannot be. Negative pi cannot be. 2 pi, 3 pi on both sides. So those are the numbers that cannot be in the domain. So as a result, you're going to have a bunch of vertical asymptotes. We're going to have vertical asymptotes. Okay, so let's practice this. So I'm going to draw the vertical asymptotes and you're going to do some markings with me. Okay, so at the same time, we get to review some of those algebraic basics. We're going to review those algebraic basics. Okay, so I'm drawing those. Vertical asymptotes. These times the vertical asymptotes are not at odd number multiples of pi, but at k pi. So that's one of them. Hold on, I need to change the color. Okay, I need to change the color. And this one I'm going to make it a little thicker. Wait, I need that to be broken. Right, so that's, what is it? Oh, never mind. I need to adjust the view. I need to adjust the view. Okay, so let me adjust the view. That's why. Okay, wait a second. This is not broken. I'm gonna make it green. Okay, the red is the red needs to be broken. Okay, the red need to be broken. That's one of the vertical asymptote. Okay, so I want you guys to give me the equation of those lines. Okay, so I'm going to draw a few more vertical asymptotes. And your job is to mark those, to mark those points. Mark some points. I'll tell you what points I want you to mark. Okay. I want you to tell what points you want to mark. And the forbidden, right? Recall that A cannot be k pi, right? So where are k pi? When k is 0, that's 0. When k equals to 1, that's pi. When k equals -1, that's negative pi. So we have all these vertical asymptotes for cotangent. We have all these vertical asymptotes for cotangent. So the pieces are between the vertical asymptotes, right? And of course, you can imagine we're going to choose the simplest one. But before we move forward to choose the one we want, I wish you guys to give me some markings, give me some points. Okay, can you mark these points for me and give me the line equation, the vertical line equation? Okay, so I'm going to call this point capital A, and this point is a capital B, and that point is a capital C. Okay. That C is a little too close. Okay, capital C. And what is the line equation, the vertical line equation I want you guys to give me? Okay, so this line, I call it lowercase a, and this line called lowercase b, and this line is called lowercase c. Can you give me the line equation of the ABC and the points ABC, the coordinates of ABC? For example, A is what? I'm sorry, B. B is what? 0 is 0, right? 0, 0, that's origin. I'm doing the easiest ones, and you are doing the hard ones. You're doing the hard ones. 1 minute, 2 minutes. Can anybody tell? But you also need to give me the equation for B, okay? The equation for this vertical line. Can you give me that equation for the vertical line? ABC. Line equations. So let me specify, okay? Please give equation of the red vertical lines and next give coordinates of the points, of the red points. Can you mark those? Okay, Kelly marked. Negative pi 0, A, C is pi 0. Perfect. Very good job. Very good job. Okay. A is negative pi 0. Wonderful job. Okay. So that's negative pi 0, comma 0. And the next point, this is a pi, comma 0. Wonderful. And Hazel says lowercase a equals to negative pi, b equals 0, c equals pi. That is to be discussed, Hazel. Okay. Riley says x equals to k pi, where k is an integer. That's but in the specific case, Riley, you're close. But in the specific case, so a equals to x equals, that's right. That's better, Kelly. X equals to negative pi, b is x equals 0, c equals to pi. That's wonderful. Okay, that's wonderful. Hazel's question needs to be modified because a as a line equation, you have to express it as either x equals something or y equals to something or y equals mx equals b. Okay, so you have 3 forms to choose from. Okay, either x equals something or y equals to something or y equals to mx plus b. Okay, so for these lines, for any line equations, you have 1, 2, 3. You have 3 to choose from. You have 3 to choose from. But we need to understand line equation. A line equation, let me write it down, okay? A line equation is a description of common feature or features of all the points on the line. That's the essence of line equation. That's the essence of line equation, okay? That's the essence of line equation. The line equation is a description of a common feature of features of all the points on the line. For example, if you recall what you learned in elementary algebra, right? Y equals mx plus b. What is m? M is the slope. M is the slope. That slope is the same between any 2 points you choose on the line. That's the common feature. And B is the y-intercept. B is the y-intercept, right? You understand that. But sometimes for a horizontal line or for a vertical line, okay, horizontal line can fit in this form, but vertical line does not fit in this form. Why? Why? Take this the vertical line A, for example, right? If I mark all the points, if I mark all the possible points, I'm going to mark a few. Right? I mark the points on this vertical line, right? What do all these points on stars have in common? What do they have in common? Their x coordinate is negative pi. Y coordinate in this case is a positive number. The next one is negative pi. And it's a positive number, different from the one before. And this one, negative pi, positive number, right? These three positive numbers are different, but all 3 points share the same x coordinate, and keep going. This point star is also negative pi, but this time the y coordinate is a negative, different from all of the above. And this point, negative pi, and the negative y value. Okay, all of these points and more on this line, they have something in common. What is that common feature? What is that common feature? Their x coordinates are all the same, negative pi. How about the y coordinates, right? The y coordinates obviously are not always the same, but they have something in common too. What is it? It's y can be any real number. You can go as high as possible. You can go as low as possible on this line. So y, in a sense, is free. What does it mean a variable is free? If a variable is free, it's not going to show up in the equation. Okay, therefore, the equation of line A will be the same as what is being described by Kelly. Okay, Kelly said x equals to negative pi. That's a perfect answer. That's a perfect answer. And you can see that equation is x equals to negative pi. Okay, and x equals to negative pi, this is the description of common features of all the points on the line. Do you guys see that? That's what I meant, okay? B, Kelly's answer on B is also correct because all of these points, okay? The points can go as high as possible, as low as possible, but all of these points, what do they have in common? The first coordinate, x coordinate is 0. X coordinate is 0 for all of these points. Do you guys follow me? Read that sentence one more time. the sentence I have written down on the screen. A line equation is a description of common features of all the points on the line. And if I change the line to curve, okay, a curve equation is a description of common features of all the points on the curve. That will still be true. That will still be true. Okay, so the common feature of all of these points, okay, y is free. So these numbers can be any number, freedom. And therefore it's free, it's at large. It doesn't show up in equation. Because from another perspective, equation is seen as a constraint. Okay, you have to be here. You have to be here. When you don't have to be here, you're free. So that common feature, like Kelly just described, is x equals 0. X equals, so this vertical line, which is also y-axis, right? That equation is x equals 0. So y-axis equation, line equation of y-axis is x equal to 0. Do you guys follow me? And how about C? Okay, Kelly already gave the answer. That answer is also correct. Okay, so I'm not going to explain any further because it's similar ideas. Okay, it's a line equation that's a description of common features of all the points on the line. So please write them all down here. With that said and done, with that said and done, we know that cotangent is not a one-to-one function. Okay, cotangent is not a one-to-one function. Since cotangent is not a one-to-one function, right? Since the cotangent is not a one-to-one function, it doesn't have the inverse. So what can we do to make it have the inverse? We're going to use our old trick. We're going to use our old trick. Truncation, right? Find the no-fly zone on the unit circle. And we will have an inverse. We will have an inverse. So which interval, which piece will be the piece of our choice? The piece of our choice is this piece between 0 to pi. This is why I want you guys to mark the points. Okay, between 0 to pi is a piece of our choice. How about the rest? The rest are truncated. Chop, chop, chop. Okay, chop, chop, chop. And next, did you guys write it down? The whole thing? So now, next, that truncation takes place, right? Truncated. Cotangent. Okay, truncated cotangent. What do we have? And of course, it's going to be different, right? What would that be? What would that be? I'm going to truncate, okay, by limiting the view. Okay. And there. That's the piece we have left, okay, after the truncation, between 0 to pi, And this is the cotangent with truncation, and how do we specify it? What is the otherwise specified? The otherwise specified will be A is going to be from the interval from 0 to pi. Can we include 0 and pi? Of course not, because cotangent is not defined there. Those are the points that cotangent is not defined. That's why we have those vertical asymptote. So now this function is 1-to-1. Okay, so once again, we're going to call it G, right? So the same practice. So 1-to-1 function, it has an inverse. And that inverse we're going to call G inverse. G inverse, right? G inverse will take ratio and produces what? Going through that G inverse produces angle. Oops. Produces angle. Okay, so let's look at the description of these two functions. Let's look at the description of these two functions. So ArcCotangent, okay. Actually, I'm not sure if the software will graph it for us, but anyway, we're gonna do it, okay. So this piece has inverse. So what the description about this this piece, right? We have the domain specified and range, right? Range. The range is, of course, from negative infinity to positive infinity. Okay, so it's inverse. It's inverse before we even give a name to the inverse. What will be the domain and range of G inverse? What's the domain and range for G inverse? One's domain is the other's range, right? Domain, range. So this is the range of G. So the domain for G inverse. The range for the domain for G is going to be the range for G inverse. So that's how the domain range is set. Domain range is set. Okay, you can plot points. When this time you plot points, it will be the orange. So this time I'm only going to plot 1 point. Okay, we're not going to do the do too extensively, right? For example, cotangent pi over 4. I will give you homework for you to do that, okay? But I'm not going to do it in class. Cotangent pi over 4 equals to 1, right? But this time it's going to be the red number divided by the blue number, okay? It's the red number divided by the blue number. Red divided by the blue. Okay? On the unit circle, on that unit circle, okay? So let me bring that up. Where's my unit circle? Hello? Come with me. Okay, so come with me. Did I put it on the top? Yes, I did. Okay. It's the red divided by the blue. Okay. Because this is from 0 to pi, because this is from 0 to pi, right? Because this is from 0 to pi, not including 0 to pi. Therefore, what is a no-fly zone? No-fly zone at the third quadrant or fourth quadrant. And the angles are always going to be positive because it's from 0 to pi. Okay, from 0 to pi. So that's how, you know, if you understood all the things we have done, you know, previously, then this is going to be, you know, come naturally. Then when I plot the points, right? When I plot the points of input pi over 4, output 1, so I will have a point over here, okay? Pi over 4, comma 1, okay? I'm gonna make that point, of course, is green. That's the point, okay? To understand the point, okay? Very similar, okay? I'm gonna use orange color, okay? You know what that orange color means, right? What is that orange color? What does that orange color means?
Arc length.
That's right, right? Now I'm going to use that orange color again to describe pi over 4. Okay, wait, doesn't show me. Pi over 4, make it thick. Do you see that orange color? Okay, let me remove that thing. Do you see that orange color? Same thing, right? You see all of these orange colors consistently show up in our function, right? And this, the ratio is a cotangent ratio. It's a red divided by blue. It's a red divided by blue. So let's see what color I should use for that. Okay, what color should I be using? I don't want to use that purple. I don't want to use that purple. Okay, purple is being used, right? So let's see what color shall we use? What color? We have used the blue, we have used red. What color shall we use? Maybe pink? What do you think, pink? Let's try pink. Okay, so that's ratio. You can also do the points. Okay, I will put that on your homework for you to do. Okay, I will make that table for you to do on your homework. Okay, so now with this function, we're gonna have a inverse. We have an inverse. Okay, so let's draw the inverse, right? Let's draw the inverse. It's at our fingertips, but sometimes some of the software doesn't produce it. ArcCotangent. Let's see if it produces a curve for us. Oh, there. It doesn't actually. ArcCotangent. You see, this software doesn't produce ArcCotangent. What a shame. What a shame. But that's okay. I know there's a place that produces it. Okay, I know a place that produces it. So that's our okay, I'm gonna bring that to you. Don't worry. If you have a calculator, your calculator should produce it. Okay, decimals. That shows that you can see ArcCotangent is not always used. It doesn't use, it's not used very much. Okay. ArcCotangent. There. Okay. So 0. Y equals 0. Y equals to pi. Okay, so I have it produced. So I'm going to show it to you. This is on decimals. That's the ArcCotangent. That's ArcCotangent. Okay, and I can put the steps there. Okay, so that's the ArcCotangent. Okay, do you guys see that? Unfortunately, the software I use, it doesn't produce that, but that's okay. We got it somewhere, right? We got it somewhere. So I'm going to use this. I'm going to bring that picture to this, to our. Okay, we're going to bring that picture over here. To our study, and then we're complete, right? And we're complete. There. ArcCotangent. ArcCotangent. Okay. So I'm going to copy this picture and bring it to our need, which is, whoops, sorry. New share. All right. So that's ArcCotangent. Okay. And these, the blue and the green, they are the horizontal asymptotes. These are horizontal asymptotes, okay? And I will give you homework for doing some points. You will encounter ArcCotangent, but not as often, may not be as often as the ArcTangent, but you may still encounter it, right? So how do we read that picture? How do we read that picture? Here we have the orange and blue. So let me put this on the side. Right, we have the orange and blue. On this picture, what is the orange? What is orange? What is the pink? I mean, orange and pink. What is orange? What is the pink? Right? We understand. We did 1 point for tangent, right? And how about ArcCotangent? Right? So we have an example in this picture. We have tangent pi over 4 equals to, so let me put it over here, right? So we have an example of a tangent, I'm sorry, ArcTangent, right? Cotangent of pi over 4 is equals to 1. For the ArcCotangent, right? So this is ArcCotangent. ArcCotangent would do what? ArcCotangent. Oh, okay. So this is an example, right? ArcCotangent will take 1 produces pi over 4. Produces pi over 4, right? So where is that point? Where is that point? Okay. I certainly cannot draw like I did here, but I'm going to draw it over here. I'm going to do the best I can to draw this. Okay. So what is ArcCotangent 1, right? This is ArcCotangent curve, right? So what I'm going to do, I'm going to use my, does this look like a pink? That's not pink. Okay, so suppose that's my pink. Okay, pink. Okay, the pink is 1. So this is 1. And the orange, that's the orange. Orange is pi over 4. Orange is a pi over 4. Do you guys follow me? This orange is the same as this orange. This pink, okay? This pink. Just tell me this is a pink. Okay, I know this looks like purple. This pink is the same as this pink. You follow me? That's how you read the graph. This is from angle to ratio, and this is ratio to angle. Do you follow me? So far, so good? Okay. You will have homework. You have 2 tables to work with on ArcCotangent today. I will get them out. And, but I think that's about what we're going to do. And let's look at some exercise in trick 7A. Let's look at some exercise on trick 7A. Shall we? Are you guys ready? All right. So if you have any questions, and please bring them all up here, right? So we have ArcTangent. We get some valuable information, right? So we can even put the pictures in our, we can even put our pictures, right? This guy is one of the pictures, right? We can put it over here. That's the after the truncation. And we also have the ArcTangent, which is right here, right? And we wish to bring it up here, right? So, and the tangent, of course, the tangent we know of, I'm sorry, the cotangent, of course, we know of is the one that's, the cotangent we refer to is this guy. I hope that's clear to everyone. Is that clear to everyone? Is that clear to everyone?
Yes.
Okay, thank you. Okay, so let me make it a little smaller so you can see everything. Right, you can see everything. Cotangent is a cotangent we refer to with domain range. And ArcCotangent and the first cotangent on the first column, they're not inverse to each other. Okay. And the last one is the inverse function to ArcCotangent. But this latter one is often not explicitly mentioned. So anytime you see cotangent, unless otherwise specified, okay, so we're going to talk about the unless otherwise specified one more time, right? We refer to this cotangent, so they're not an inverse function to each other. Okay, so that's the summary of ArcCotangent. So next, with this guy as a G inverse, okay, we're going to work some exercise in trick 7A, right? And this is our G. Okay, so let's look at that amazing property about inverse functions, right? F and F inverse are inverse to each other, okay? Which implies one's domain is the other's range, vice versa. And we know that this is always true. This is always true, right? For what? For what kind of X? For X in the domain of F inverse. F inverse. Okay, so I need to make it larger. Otherwise, you don't see the negative sign. Is that better? Okay, so once again, we've done this many times, right? So the next one is F inverse of F of X is equals to X for X in the domain of F. Right? So that property still applies here. It's eternal. It's eternity. It's for eternity, right? So it works for G. This applies to G and G inverse. It's just a change of name. It's just change of name. Okay? So as a result, we're going to change the name to G inverse, G inverse, and this is a G inverse, and that's a G. Do you see that application, right? And furthermore, that is, we're going to put a G in place. We're going to put the G in place. What is that G in place? G. This is the G with a specified domain, right? This is a G with a specified domain. So this G is cotangent. G inverse, ArcCotangent. Okay, ArcCotangent, ArcCotangent. Okay, and we can remove this parentheses. For X in the domain of G inverse. What is the domain for G inverse? The domain for G inverse is right here. Right? Now G inverse is ArcCotangent and G is cotangent. We can remove that parentheses for simplicity. And this X is in a domain of G. What's the domain of G? Domain of G is the range of G inverse. So that piece is replaced by that. And that is the fourth property on the fourth row, in the first table of trig 7a. Okay, the fourth row in trig 7a, first table. Do you guys see that? And once again, this is true for any real numbers. So when you encounter that, it's always true. It's always true. But what it makes people tend, what people tend to confuse is that especially you don't often use it, right? When you don't often use it, if you know the process, you can quickly figure out yourself because you can just punch in the calculator, see the curve, identify the points, and you get the domain and range and the domain of inverse, and you're all set. You just have to know how to apply it, okay? So let's look at a couple exercises. So this time, we're going to just do some exercise on these things we have just gone over on cotangent. Okay, so let's look at trig 7a. We not only apply these because sometimes these are applicable, sometimes they're not, right? So let's look at a couple of cotangent. Let's look at a couple of cotangent. For example, 28. We have a cotangent, ArcCotangent of 5. What does that equal to? What does that equal to? The first property applies, right? The first property applies. So it equals to 5. Equals to 5. Or you can go the DRA, ARD that way. Okay, you can go that way too. You can go that way too. Got it? Any questions? Any questions? Do you want me to go over that DRA, ARD thing? Because that part is very important, okay? You need to use it for Calc 2 in integration part, right? Sometimes you get to apply those. You want me to do that? Okay. How do we do that? Okay, so if you know this property, great. If you don't know this property, what is your primary resource? Right? You start with definition, as always. Definition is our sole source of everything. Everything, absolutely. I couldn't emphasize that enough. Okay, definition give me as a teacher confidence, assurance in teaching. Okay, even the unit circle is not that essential. Even the unit circle is not essential. So ArcCotangent, right? So I know ARD, right? I know ARD. So ArcCotangent. Okay, so from ArcCotangent, I basically know what? I know ARD. I know the D. I'm looking for what? I'm looking for A. ArcCotangent also tell me the range of ArcCotangent is what? The range of ArcCotangent tells me what? Okay, when I talk about this, I also, I'm preparing you for trig 8. I'm preparing you for trig 8, okay? So ArcCotangent of no matter what, okay? You look at the range of ArcCotangent, right? What does that tell you? No matter what, is the input, because the domain of our cotangent is negative infinity to positive infinity, right? So no matter what, ArcCotangent is going to give you a value between 0 to pi. The range is is 0 to pi. That's what it tells us. That's what it tells us. Do you guys see that? That's what it's telling us. You could make that sentence one sentence statement about ArcCotangent. That's what it means. No matter what's the input, the output is always between 0 to pi. Therefore, this quantity is between 0 to pi. It's an angle measured from, if you talk about A, ArcCotangent answer, right? If you measure any angle, your answer is going to be not from 0, a little bit more than 0, counterclockwise measurement. Your answer is always going to be positive. ArcCotangent always give you a positive angle. It doesn't matter degree or radians, depends on what you want, but it's always between 0 to pi, right? The third quadrant and fourth quadrant, no flight zone, right? No flight zone. So with that said and done, we know that cotangent in the first quadrant is positive, in the second quadrant is negative. So now we have a ratio of 5. We have a ratio of 5. 5 is positive. So the terminal is going to be where? The terminal is going to be in the, where is it going to be? It's going to be in the first quadrant. It's going to be in the first quadrant, okay? It's going to be in the first quadrant, okay? I don't know where. It's not a special angle, but the information tells us that a cotangent ratio is what? That cotangent ratio is what? Is 5. What is a cotangent ratio? Cotangent ratio, in definition, okay, you pick any point on the terminal sides of the angle other than the origin. Does that sound familiar? I'm quoting the definition. I'm quoting the definition. And this point has xy. xy. Okay? And what is x? This is x. Right? The red. I'm sorry, why did this come? The red, give me the red, okay? Give me the red. The red and the blue. Red and blue refer to that unit circle, don't I? Okay, red and blue. And that ratio is 5 to 1, right? Because 5 is the same as 5 to 1. What does that tell you? You can safely assume this is a 5. This is a 5, the red is 5. And the blue is 1. That's adjacent sides over opposite side. Definition, you guys follow me? 5, 1. You can find the hypotenuse if you want to. Okay, 5 squared plus 1 squared is root 26. They're not special angles, but it's all within your control. It's all within our control. So 5, 1, this 1 should be a blue if, you know, if I want to be consistent, right? This is a blue 1. Okay, you can do, you know, you can, at this point, you know everything about this triangle. You know everything about this triangle. You can get sine, you get cosine and everything, right? So this angle, you're going to take cotangent of this angle. So the same angle, right? So how do you find cotangent of this angle? You take the adjacent side, divide by the opposite, 5 divided by 1. So what answer do you get? What answer do you get? What answer do you get? We already got the angle,
divided by 1
right?
is 5.
Is 5, right? 5 over 1 is 5. Therefore, you draw the same conclusion. even if you don't know these special formula, but if you just know ARD, you know the range of ArcCotangent, and you know the domain of ArcCotangent, you can see we've been focused so much on domain, range, intercepts. Aren't they important or what? What do you say to me? Important, right? And you have to use it every day. You are going to use them on daily basis every single day. You can choose not to use it. That means you're going to lose points left and right, okay? Period. All right. So we know some perks and tricks, but the fundamentals is still ARD. Okay.
Professor, I have a question about the graph. So the y is what? Is 2 or 1?
Y is 1.
Okay. On the graph, it looks like 2. I was confused.
What are you confused about? 5
Um,
equals to 5 divided by 1. It's a ratio. It's a ratio.
okay.
It's a ratio of the blue, the red number over the blue number. So that's how we get the 1. 5, 1.
I think
Right.
she's just
Sir,
confused because
yeah.
it goes up to
Is that
the
clear?
graph.
I'm sorry, go ahead.
I think she's confused because it goes up to 2 on the graph.
Oh, oh, sorry about that. Just ignore those numbers. Okay. Don't look at these numbers. Don't look at these numbers. All right? Don't look at these numbers. Is that what confuses you?
Yes, thank you.
Okay, just don't look at those numbers. We're not drawn to proportion. But I cannot get, I don't know how to get rid of them. All right? So that's 5, that's 1. It's good you pay attention to it. It's a good thing. Sometimes you do need to attend to that, but sometimes they're actually cumbersome. All right. Any other questions? Okay. I think this is a pretty good, a decent coverage. Okay, this is a decent coverage. So you can do these things. The primary thing I want you guys to walk away with that the definition, that definition we have been on for weeks, right, is the centerpiece of trigonometry. Now you must agree with me. You must that ARD is the 3 pillars of trigonometry. Do you agree with me? Yep. You need them all the time. You need them all the time. You have to be aware of them all the time. Okay. Thank you. All right. Next. So the ARD is your ultimate tool. Okay. So let's do just some other exercise. Okay. And then it's about time to wrap up. Okay. So for example, number 34 is easy, right? 36 and 38. So how about we do, let's do 32. How about that? So, okay, 32. Okay, 32. 32 is arc cotangent of negative pi over 6. Because this is a special angle, so we can borrow our special angle. We can borrow our special angle, right? We can borrow our special angle. Even if it's not a special angle, even if it is a special angle, you don't have to use this thing. You don't have to use that. Okay, you can still use this guy. You can still use this. Okay, the blank, which may give you more freedom. Okay. All right. So arc cotangent and cotangent negative pi over 6, right? Does any one of these two properties apply? This one cannot apply. Does this one apply? Does this apply? Does it? Does it apply or not apply? Well, to apply, this angle has to be positive, right? Between 0 to pi. Obviously, it doesn't apply, right? Does not apply. And then what you do? We have to do it from inside out. Inside out. Okay, from inside out. Okay, so step 1, we do the inside. And step 2, right? So cotangent negative pi over 6, you're going to measure clockwise. Boom. That's a terminal. You take the red number divided by the blue number. That's a cotangent. That give you the cotangent ratio. So we have ArcCotangent. The parentheses, what do we get if we divide by red by the blue? Negative root 3. Negative root 3. And then what? And then what? Then what? We have ArcCotangent negative root 3. ArcCotangent is defined on all real numbers, right? So this should be giving us an angle. But this angle has to be between 0 to pi. So what else ratio will give? What else ratio will also give us? What else ratio will also give us? Negative root 3. We have 1 over here, right? We have 1 over here. Wait, doesn't work very well. Wait, go. Okay. So this ratio give us the ArcCotangent negative root 3 ratio. What else give you our, the similar ratio? Red divided by blue, this guy, right? Yes? Yes?
Yeah.
Right? But this terminal falls on the no-fly zone because ArcCotangent does not fly over quadrant 3 and quadrant 4. So what will be the ArcCotangent angle? The ArcCotangent angle is going to terminate here, right? That's from 0 to pi, right? That's from 0 to pi. So what happens on the other stuff? They are on the no-fly zone when ArcCotangent is mentioned. Now, how do we measure this angle? From the standard position. Boom. So what do we get there? What do we get there? We should get 5 pi over 6. In a way, this part is very similar to cosine. It's very similar to cosine. Okay, not exactly the same as a cosine, but very similar to cosine. Okay, you need to understand that the range of ArcCotangent is from 0 to pi, inclusive. The range of ArcCosine is 0 to pi. I'm sorry, inclusive. Our ArcCotangent is exclusive. Sorry about that. So ArcCotangent's range is from 0 to pi exclusive, excluding 0 and pi. ArcCosine, the range is between 0 to pi, inclusive, including 0 and including pi. You can follow me? Otherwise, everything else is similar. Everything else is similar. Okay, you need to understand that no-fly zone when you deal with ArcSine, ArcCosine, ArcTangent, and ArcCotangent. Okay, and I think you guys got it, right? You just have to practice some more. Okay, so let's review the no-fly zone for all these 4 arc functions. Shall we? You want that or you got it? No-fly zone. Okay, so all 4 functions, right? ArcSine, ArcCosine. Summarize. Okay, so ArcSine. Okay, ArcCosine, ArcTan, ArcCotangent. In terms of domain, you know what I'm going to do is I'm going to rearrange it in this way. So this, hopefully this will help you, okay? So I'm going to put ArcCosine on here, okay? ArcTangent on here. The domain for ArcSine is between -1 to +1. You have different forms, right? We have different forms. For cotangent, it is ArcCotangent is the same. Okay. For ArcTangent, the domain is from -infinity to +infinity, and that's the same for ArcCotangent as well. The range, however, for ArcSine is going to be from -pi/2 to pi/2. For ArcTangent, okay, it's just the bracket, it turned into parentheses, exclusive. You follow me? ArcCosine, the range is to 0 to pi, inclusive. The range for ArcCotangent is 0 to pi, but exclusive. Okay, I hope this will help you to understand and maybe to a certain extent making connections. The last thing you want to do is memorizing. Okay, the last thing you want to do is memorizing. Do you think this is helpful? Now, we have 5 minutes left. Your time, okay? And I have a brief announcement about the midterm next week. I told you yesterday I'll be out on medical leave from 27th to tentatively, okay? The date of surgery hasn't been completely set, but it's going to be the kind of surgery I have is called hysterectomy. It's a treatment for cancer, okay? All right, so I will be tentatively gone from 27th, okay? But that's to be confirmed next week, okay? And I know you guys, some of you have, you guys have some concern when a sub is identified, and I hope we can identify that substitute before I go into surgery, that I will tell the sub what I have done, how I have done it, and all the materials. I will make sure they are available to you that I have produced and for this semester and the last. But once I take over, when I have hand over everything to the substitute, then it's just going to be up to them, up to him, how to teach or how to him or her. Okay, how she teaches or he teaches in whatever way. I assure you that teacher is going to be qualified to teach this class. So don't worry about that. We may have differences in styles or emphasis, but you will be in good hand. Okay. And next is about midterm next week. Okay. The midterm, there will be no quizzes next week. And the midterm exam will be given to you, will be available to you from Friday to Sunday. Friday to Sunday. Okay, 3 days. Okay, so from the morning of Friday till midnight Sunday. So you have 3 attempts to do that magnified quiz. Okay, the style is very similar to the quiz you have always been doing. So if you watch the lectures enough time, practice enough time on my lectures, you should be okay. You should be okay. You've done all the quizzes and all of that stuff, you'll be fine. How much time I will give for each sitting, I have not decided because the exam is not completely ready. Okay, it's not ready for you yet. So I'm still working on it, but I will give you a definitive answer before you start taking that exam. All right, so after I leave, but I will complete, make sure the gradings and everything is done before I go in surgery. But I will be here until the 26th. Okay, so take advantage of me. If I can help you in any way, I will be happy to. And but I most likely I won't be back after the surgery because I will have 6 weeks of period to rest according to the doctor. And after that 6-week period, it's already the end of the semester. Okay. So I assure you, you guys are going to be in good hands. And next semester, actually, I'm also teaching 2 sessions of Math 180. I'm teaching 2 sessions of Math 180. And thank you so much, Angelica. I'll be teaching 2 sessions of Math 180. Whether you are going to be taking calculus or not in the spring semester, you are welcome to ask me questions and come to my classes. I have 1 class online and 1 class in person next semester, in spring semester. And the good thing is that I will make sure Farouz is still going to be with you guys. And I'm sure that's not going to change. So Farouz will be the one that is familiar with what I have done. So you have, a TA that's familiar with everything I have done. So he's going to help with the new teacher to complete the rest of the semester. I kind of give you some heads up because I'm anticipating this surgery. I personally, I'm sometimes I feel scared, who doesn't, right? But anyway, I hope that everything will be fine. Thank you, Kelly. But I still treasure the amount of time I still have left with you guys. And I very much, I will be missing you guys too. I will really miss you guys, especially if I recover sooner. If I recover sooner and I feel good enough, and I think I'll be fine. I'll be fine after this, after all of these, and I will surely be back in the spring. And I'm hoping that I don't have to do the chemo. And by all accounts, it seems that there's a highly likelihood I don't have to do the chemo. No matter what, thank you. I will be looking forward to see you if, after 27th, right? 27th and after, I'll be looking forward to seeing you guys, on campus, right? In the spring semester. Okay, so you have time and come say hi to me. But still, we have next week and 2 more days after next week. So this is just to give you a heads up. If you have any questions, so please just don't hesitate to ask me.
So Professor,
yes,
thank you giving us notice advance. So we can download your rest of the video lecture
Right.
from now until end of semester, right?
Yeah, they will be available because I made them available on YouTube. Once you have access to YouTube once, you have access to all of it because there has an account name and stuff like that. So you can just make it, you know, I think if you subscribe, I'm not clear about that. If you subscribe, they will keep popping up in front of you, I guess, until you get tired of it. Is that right? Probably.
I don't know, but we have a few options. One of the option is there are softwares we can, you know, record the screen free of charge. And that is one of the options I have heard. But as you said, YouTube is another option. So if students want to continue your style of teaching, they can, you know, watch all those remaining of the
Yeah.
lecture.
Absolutely, they're all there already, including materials I have covered in this class, and all those videos I have uploaded on YouTube, and they're all public in the public domain. You can see the lectures I'm going to cover had I not had to go to the hospital, and you will see those, you know, on other topics. You're gonna see them, okay? And you just look through the. Actually, I don't know how my account look like. I put it there for your convenience, but I'm not a technically so savvy about, you know, organizing those well. I just put them out there for yeah, thank you, Winston. I appreciate that. Yes, what I wish to tell you is that thank you so much, Winston. I want you guys to continue to keep on going and do well on this course, so to eventually finish your academics requirement and be successful in life. And I will surely miss you guys. And you know, teaching is a thing I want to do, I ever want to do for my life. And to be away from teaching certainly is hard, but you know, and I'm glad I can be of some help. All right.
Professor,
Yes.
did you say you were teaching pre-calculus over the spring or just calculus?
No, I will be teaching 2 sessions of pre-calculus in the spring.
Oh,
Pre-cal. So if you guys get into calculus class, you may still have questions about pre-calculus or calculus. You can also seek me out. I'll be happy to help.
oh, okay. Thank you.
Mhm. I appreciate you guys, you know, kind words. And but I will see you guys on Monday. I will see you guys on Monday. Okay. I will still be here.
Thank you very much, Professor. Have a nice
Thank you,
weekend.
everyone.
Hey,
See you Monday.
Professor,
Yes.
even though you are leaving, well, the class is still going to say synchronous, right? Like we still have to meet up on Zoom.
That's the part I will make sure you know before I leave.
Okay.
I hope that will be synchronous, but whether it is going to be asynchronous or synchronous, that's up to the dean and the availability of a substitute.
Oh, okay.
Yeah.
Thank you.
Mhm.
Thank you for the lecture, Professor.
Of course, anytime.
Thanks again, Professor.
I
Take
will miss
care.
you guys terribly after that. Okay, have a great weekend. Bye.